Welcome to the channel. Today we are going to discuss about time value of money. Everybody understands that receiving $1 today is much better than receiving $1 tomorrow or next month or next year. So money depends on time. We will discuss interest rate, future value of cash flow, present value of cash flow, effective rate, and internal rate of return. So this reflects the time value of money. Simple interest rate. Let's say we deposit $100 with interest of 8% for 4 periods. This period may be 4 years. So this $100 becomes 108, then 116, then 124, then 132. In general, 100 multiplied by 1 plus 4 times R. So generally, we can define the simple interest rate as if A is invested for any period, the simple interest of R, the value at maturity or at final time becomes A multiplied by 1 plus R. The other thing is about compound interest. Again, let us start from example. With the same interest rate, R is equal to 0.08. If we deposit $100, then after a period 1, we will have 1 plus R times 100. In the second period, as you can see from this derivation, you'll get 100 multiplied by 1 plus R squared. In the same way, we can proceed this step, then 100 multiplied by 1 plus R to the power of 3, and so on. So at period 4, you'll get 100 multiplied by 1 plus R to the power of 4. Generally, with a deposit A with interest rate R, then the value at maturity will be equal to A 1 plus R to the power of N. The other point is compounding with multiple periods. That means N is compounded period or year, R is annual interest rate, A invested for Y years yields that A multiplied by 1 plus R over N to the power of Y times N. For example, $100 invested at 8% for 2 years with quarterly compounding. N is equal to 4, that means. Then the money grows in this way. For example, at the 4th period, that means after 1 year, it becomes 108.24, and so on. This will be the process. So finally, after 2 years, that means at the 8th period, you will get 117.17. So this is the general formula. So the application is that in banking, valuation of bonds, investment, and so on. Continuous compounding, it corresponds to when the time period is closer to 0. That means when we take the limit of this quantity closer to, when n is closer to infinity, you'll get A e to the power of R times Y. And here the graph indicates how the money grows through time. And the quantity E is an irrational number, which is approximated by 2.7183. So it is derived by this special limit. Comparison of this different compounding. Here this table indicates for annual compounding, quarterly compounding, monthly compounding, and continuously compounding with these parameters. So as you can see, the continuous compounding is a little bit larger, but not significant for this 5 years with this parameter. The next point is the future values of cash flows. For instance, consider a 10% interest of this cash flow, which is indicated on this timeline. So the future value can be calculated using this formula, and you can see that you can work by yourself. It is equal to 171.3. So generally, if given a cash flow of a stream, which is indicated C0, C1 up to Cn, with interest rate R per period, then the future value of the stream is given by this formula, and using the summation notation, it can be described by k from 0 to n, ck 1 plus r to the power of n minus k. This is applicable in these areas. Present values of a cash flow. The price P of a contract that pays a cash flow stream of this kind, C0, C1, C2 up to Cn, where C0 is positive, it is cash inflow, and when C0 is negative, it is cash outflow. Then the present value is given by this formula with this interest rate. PV is equal to the summation k from 0 to n, ck over 1 plus r to the power of k. Here 1 over 1 plus r to the power of k is a discount factor. For example, here the cash flow starting from 3000, then negative 1000, 1000, and the present value using the above formula can be calculated, and the net present value is indicated here. Effective rate, the simple interest rate that produces the same yield in 1 year as compounded interest. If the interest is compounded m times a year, the effective rate must satisfy the following. That means a times 1 plus RE equal to a times the compounded interest. After rearranging, you'll get this formula. For example, consider this interest rate compounded 12 times. So you have the effective rate is equal to here. Internal rate of return. If a cash flow stream is given in this way, then the internal rate of return is the stream is a number R satisfying this equation. It is independent of the prevailing interest rate and depend only on the cash flows. The internal rate of return can be used to rank alternative cash flow stream. The higher the IRR, the more desirable the investment. A project is not worth considered unless its IRR is exceeding the prevailing market rate. For example, here C0 is equal to minus 100 and C1 is 120, then the internal rate of return can be calculated in this way, which is equal to 20%. Thank you for watching. Subscribe for more on quantitative finance and maths. Thank you.